Okay, thank you very much. Thank you very much for the invitation, Fabien. It's very nice to give you this opportunity to share with you what we have done during the nearly 2 years on this program. I belong to the Société astronomique de France, the French Astronomical Society, which is an old society dedicated to astronomy, founded by Camille Flammarion 140 years ago, so an old lady. And during the last 5 years, I lead a group with between SAF and Société Française d'Astronomie et d'Astrophysics to develop citizen science collaboration. And once a year, we organize a workshop during the SF2A meeting at the end of June or beginning of July. And during the last 2 events, Fabien, Attila went to present Astro-COLIBRI. And of course, he discovered the RAPAS program. The RAPAS program is a program which has been funded by the Paris Observatory. 2 years ago, Paris Observatory introduced a call for proposal for collaboration between amateur and professional to fund development, to fund new components, and to bring to reality so dreams for amateur astronomers. William Tullio from Paris Observatory IMCCE is a PI. I am the co-PI. Very interested due to the fact that he belonged to IMCCE, is very interested in solar system object. And Michel Denfeld from IAP, Institut d'Astrophysics de Paris, supported us also to develop the supernovae, stellars purpose on this project. And you see here the list of amateurs already delivering data to the program. So yes, so during the 2 last years, we answered to this call for proposal from the Scientific Council of Paris Observatory, and they granted us budget last year to develop a new set of filters. I will explain filters meeting the Gaia specification, and this year we funded the development of new spectrograph, low dispersion spectrograph, to deliver SED, spectral energy distribution, on alerts. So of course, I share with you the rising waves and the tsunami which is on the way of all these alerts. And as you see, so we have 3 family of targets: either solar system object, either optical alerts to perform monitoring, or the alerts coming from the multi-messenger field. From the solar system object, just one slide to share with you the challenge is also to perform the retrieval of the Gaia detection of new asteroids, and particularly Earth-grazing asteroids. And from one night to the following nights, you see the Gaia alerts, Gaia Fun SSO alerts give you a basket, which is the order of magnitude of about half arc minute by 1 degree about of field of view to hope to recover the detection performed by Gaia. But due to the fact that, you know, Gaia is scanning the full sky in maybe 2 months or 3 months, when it detects one object, it may pass again on this field of view only 2 months later or 3 months later, according to the position of the object in the field. So there is a strong interest to have this community to try to recover before being lost this pre-discovery provided by Gaia. So we have a specific website. The name is Gemini, to propose a portal for all the amateur astronomers wanted to connect to a collaboration, a French pro-am collaboration. Kilonova Catcher is one of them. And so we introduce RAPAS portal on the Gemini site. Here are the connection. Up to now, after 2 years, we have 50 telescopes registered to this collaboration. So the needs, we develop a figure of merit to clearly classify the capability of the telescope. It's not only the diameter of the telescope, but as you explained us, it's also a question of field of view. And in fact, we develop a figure of merit to quote what is the upper limiting magnitude of the telescope, what is the field of view in a square degree of the telescope, and what is, for 1 minute of exposure, what is this upper limit. And due to that, you see that even a small telescope, thanks to the fact that usually they have a short focal length, they give a large field of view, which could be 1 degree or even better than 1 square degree, as you explain us. And this is a nice thing also coming from amateur telescope. So here is the Gemini website. And if you have a new collaboration, I invite you to connect with us, with our team, and we may promote your collaboration. So here is a list of all the registered telescopes. And this telescope starts from 200 millimeter in diameter up to 800 millimeter in diameter. Here is the histogram of all the registered telescopes. You see, it's funny to see how this histogram is decreasing according to the diameter. What is the focal length and the numerical aperture versus the diameter. And it is a new thing coming from the amateur field, is more and more amateurs are using high aperture telescope with wide field of view connected to large diameter. So the induced idea comes from previous Gaia workshop. It was introduced by the Gaia catalog, which is maybe today the best catalog to perform astrometric, but also photometric reduction. And during the previous year, with the delivery, the data release of the EDR1, DR1, DR2, and now DR3, a friend in the group, Marc Serrault, performs the extraction of the Gaia catalog in a catalog called GRAPA, which is compact with the position and the 3 photometric feature attached to the more than 1 giga object spread all over the sky. As we share that in the amateur field also, it's a mess because we are using either Johnson-Cousin's filter, either Bissell filters, either now more and more Sloan filter, and a lot of amateur astronomers are using B, G, and R filter fitted to trichromy to perform to produce colored image. So the dream is coming with Gaia filters due to the fact that you see the enlarged bandwidth, and during the previous workshop with Gaia, I asked them how could we purchase these filters, because this will bring us an enhancement in our sensitivity. Thanks to the fact that the G filter, the green one, is it's wide open and fitted to the silicon sensitivity of CCD or CMOS arrays. And you have two subbands, the GBP in blue and the GRP in red, which cover, you see, more than 400 up to nearly 700 nanometers, so rather wide, twice wider than the standard filter. And the same for the R filter, which is much more fitted to an enlarged I filter. Well, it was a shame. I didn't understand that, in fact, Gaia is not fitted with filters. You know, on the focal plane array of Gaia, either the G filter, the photometric measurement are performed by the astrometric CCD. So it's the CCD without any filter, which provides this sensitivity. And the GBP and the GRP photometric measurement are performed by, in fact, these two CCD with a specific resistivity, either to enhance the sensitivity in the infrared, either on the blue and near ultraviolet band. And just in front of this CCD, you have a small prism dispersing the wave, the spectral band of any source. And thanks to a binning, a smart binning of the pixel attached to all the source, so you define the two spectral bands. And so at the end of one workshop with Gaia, I said, well, is it interesting to manufacture such a filter? Yes, why not? Yes, it's, in fact, due to the fact also that Gaia is performing photometric measurement attached to the nice astrometric measurement, and you have several weeks gap between another measurement, you may fill this gap with a measurement performed with the Gaia bands. So this is what we have performed. So the nice thing also coming from the Gaia catalog is the photometric accuracy. You achieve an upper limiting magnitude of more than 20, and according to the magnitude, you are either with an accuracy of less than 1 millimagnitude up to a 10th millimagnitude on the deepest side of the catalog. So what are the specifications of the filters? In fact, we had several meetings with Michel Denfeld, particularly, and the people in charge with the Gaia catalog, and in fact, to clearly define what could be the band. And clearly, we define the band also according to the fact that, of course, amateur astronomers are ground-based, so we are sensitive to the atmosphere. And so we want not to be too much sensitive according to the elevation of the change of the band on the UV side, and the same also on the near-infrared side, and particularly on the infrared side, you know, also we have to deal with the large dispersions of the quantum efficiency of silicon arrays, which could be either back illuminated or front illuminated. And so the sensitivity in the infrared could change the bandwidth. And so we define, thanks to Michel Denfeld, a cut-on and a cut-off in the filter band for the three filters. Here are the three filters. So you have an anti-reflection coating we have made cutting the UV, and you see the GBP band which is in the middle, and the GRP band which is a deep red, but in fact it's giving you an high sensitivity. You have it in transmission, and here at the bottom, you see the filter in the reflection. The coatings have been manufactured by a subcontractor we had from the Paris suburbs, and we manufactured 25 set of filters thanks to the funding from the Paris Observatory. Here are the exact spectral band of the what we call the A filter, meeting the G Gaia filter. And here you see the B filter, GBP-like, and the C filter, the GRP-like. And you see how we limit the spectral band. Also, a funny thing is coming from the Gaia filters, which was maybe an headache for Michel Denfeld, is the fact that you see the two GBP and GRP band are overlapping just on the Balmer H-alpha line. And so Michel Denfeld told me, well, it's not a good idea. In fact, if we could be sensitive to the Balmer line, it would be fine to be sensitive only to this line with one of the two filters. And so it's a small derogation we made in the specification of the band. You see there is, in fact, there is no overlap between the B filter and the C filter. They are just crossing at 50% of transmission. And clearly the H-alpha line is on the R filter, the C filter, and not on the B filter. We reject it. It was the specification. So in fact, we provide these filters to 25 amateur observatories spread all over France. You see here the histogram of this telescope. Most of the telescopes are 200 millimeter or above in diameter, and some telescopes are 800 millimeter. I try to monitor the availability of all these telescopes in green, in yellow, when they are performing maintenance, and in red when they are not operational. And the first thing we perform using an old paper from Sky Telescope, we use the same selected areas spread all over the three right assumptions. You are sure that at any time, at any night, you have one of these field of view available crossing the meridian during the night. And on this three field of view, we ask to the amateur to record what could be the upper limiting magnitude they achieve with the three filters. And we also try to fit this measurement with the Gaia catalog. Here is an example of such a wide field of view. It's a picture I've made with my telescope with 10 times 1 minute exposure. And I demonstrate that my upper limiting magnitude is 21, particularly in the A band and the B band, and the C band, the red filter, it's smaller, a little smaller, due to the fact that the sky background is usually more reddish, in fact, and more intensive. And here you see the limiting magnitude I achieve. And the funny thing, in fact, is on this set, I achieve a deepest limiting magnitude with a B filter, with a GBP filter. And after we perform the fitting between the measurement and the Gaia catalog, and what we demonstrate is all the observers are with a slope of, with an accuracy, you have a slope of 1, so the magnitude you measure is meeting the magnitude coming from the Gaia catalog, and the error in the slope is usually 1%. Far from this slope. And here you see the dispersion according to the magnitude we have. Yes? The parameter. So on the y-axis, this is the magnitude you measure from your picture according versus the magnitude coming from the Gaia catalog in G, in GBP, and in GRP. And of course, the signal-on-noise ratio gives you a dispersion. And the interesting thing is the fact that you detect, you see here, some funny stars, which are, you measure a brightness which are more than the brightness given by the Gaia catalog. And so maybe you detect, in fact, a variable star in the deepest side of your picture. Here are another example coming from Lisa Maris with a Celestron 11, and this is the same. We quote this activity, and you see the nice slope and the small dispersion coming from. So it was one of the first challenge. Do we are able to recover a nice magnitude measurement meeting the Gaia catalog? And the answer is clearly yes. And again, so all the observers have been tested in such a way. The second side of the second step of the program is to manufacture small spectrograph. We have in France Christian Buil, who is well known because he developed spectroscopy, and he's a good friend of mine. And he was worried. In fact, I come to here and I told him, you know, we have to decrease the resolution of your spectrograph to be able to achieve, to meet the deepest side of the detection capability with your spectrograph. And so we want to have a low resolution spectrograph. And this is what we have just manufactured. So thanks to the help also of Sheliak, we developed an ALP200. ALP600 is a well-known small spectrograph using a grism inside of the device. And so we exchange the grating, which is in fact a grism, a combination of a prism with a grating, by a grating of 200 groove per millimeter. And we develop a star X low resolution. The standard resolution is using 1,200 or even 2,400 groove per millimeter. And here we exchange the grating with a 150 groove per millimeter and what we would like to demonstrate, and we will be able to give a spectrum of any source with 1 hour exposure with a 400 millimeter telescope, and be able to achieve a spectrum on a target at magnitude 20. And Christian Buil performed some preliminary tests using a small refracting telescope, only 85 millimeter aperture. And he demonstrates with this star X low resolution that only with 8 centimeter he achieved magnitude 16. And so we are confident to demonstrate that with a 400 millimeter or even a 500 millimeter class telescope will be achieved to deliver spectrum meeting magnitude 20. So the first real scale trial we performed started in June with the supernova in Messier 101. And we start all together to monitor this supernovae. And you see here the curve we achieve in the 3 Gaia band. This is raw data without any, I would say, equation tuning according to the telescope. We use all the coming from all the telescope, the raw data. And you see here, the nice thing also is how we may draw according to the magnitude on the y-axis, the color index. And clearly we detect events in the with instability in the temperature of the source. Yes, I'm finishing. The other target we try on is a blazar, and you see also the nice thing also. So you see here the light curve with the 3 filters, and here the color index, and here the magnitude, and you see that on the blazar things are more complicated. But however, we see that we are able to detect events, very cool signature or very hot signature attached to the blazar, and according also to the magnitude variation. Okay, so to conclude, so this is the first result I am able to share with you. This Saturday and this Sunday at Paris Observatory, you are all welcome. We organize our second workshop to train our network and to share this result. And we are preparing the third year. You know, the Paris Observatory call for proposal was a 3-step call for proposal. And next year, we don't know yet what we will do. Maybe we will produce a new batch of filters because, as you understand, we are more than 50 observers ready to use, and only 25 of them are equipped with these filters. Maybe we will enlarge to an international scale, and that's why I'm here. Is it interesting for you or not? And clearly, we would like to share this new capability also with your country and with your amateur network belonging to your country. And if we are successful with a 2 spectrograph, we will define and throw the definition of this 2 spectrograph, low resolution and high sensitivity, to be able to manufacture a first batch of 10, I don't know, 20 spectrograph. Of course, a telescope which will be fitted with this spectrograph are not the same telescope than the one using the filters to complete the dispositif, the system, to be able to deliver a characterization of any target we have detected, either to reject because this is a false alarm, or either this is a relevant target, interesting, and we have to switch on a large telescope on to examine what is it. Thank you very much for your attention.